Hello everyone, I am Sadullah Çanakçı. I am a fourth-year PhD student at Boston University. Today I will present our work titled Efficient Context-Sensitive CFI Enforcement Through a Hardware Monitor. This is a joint work with Leyla Delşat Tehrani, Boyuzu, Professor Acarcuş, and Professor Manuel Egele. Writing vulnerability-free code has been always a challenging task. Considering the complexity of today's widely used applications, such as Google Chrome and Linux kernel consisting of million lines of code, this task is actually becoming more and more challenging. Attackers are trying to find several ways to exploit these vulnerabilities, and one way is control flow hijacking, which diverts the control flow of the program from its intended execution. Attackers are manipulating indirect control flow transfers in the program to achieve their goals. There are three main indirect control flow transfers in the program, which are returns, indirect calls, and indirect jumps. An attacker can exploit a vulnerability and manipulate the content of the program stack and overwrite the return address in the stack, and potentially change the execution from the intended execution. And simple scenario can be thought for indirect calls and jumps as well. Researchers have proposed several defense mechanisms to prevent control flow hijacking attacks, and in the last decade, control flow integrity has become quite popular. CFI consists of two phases. In the analysis phase, generates a control flow graph statically. Each node in the CFG represents a basic block consisting of instructions terminating with a change of flow instruction, such as branch. The edges between the nodes, basic blocks, represent the potential control flows between the basic blocks that can be traversed legitimately during the program execution. For instance, in the CFG, we label each basic block with a basic block ID, and if you look at the basic block ID 8, you will see that function pointer foo has three legitimate targets, which are function A, B, and C. And the second stage of the CFI is the enforcement stage, and at this stage, CFI mechanism collects the runtime control flow of the program and ensures that it complies with the statically generated CFG. For instance, in these examples, you see that the function pointer foo has exec as of target, which is not legitimate based on the CFG. Therefore, CFI policy will terminate this process. The success of a CFI mechanism mainly relies on two metrics, which are security and performance. Prior CFI solutions were focusing on context-insensitive CFI mechanism policies, and recent works show that this kind of policies are actually vulnerable to advanced attacks. Therefore, recent CFI works focus on context-sensitive CFI policies to provide stronger security guarantees. Context-sensitive CFI mechanisms collect additional contextual information at runtime and refine control flow graphs with this information before validating the targets of an ICT. Different works utilize different contextual information, but one quick example can be shown as call stacks. Since context-sensitive CFI mechanisms collect additional contextual information, they could potentially have higher performance overhead compared to the context-insensitive CFI policies. To prevent this and provide a low performance overhead when providing higher security guarantees, recent works leverage an existing hardware feature on modern Intel processor. This hardware feature is called processor trace. And several works several PT-based CFI mechanisms reported low performance overhead on multi-core processors when measuring industry standard Spec 2006 benchmarks, and overall the average overheads are around 10%. PT-based CFI mechanisms use idle cores in the processor to protect programs, meaning that this works use multi-core processors and assume that there will be always idle cores in this multi-core processor, which can be dedicated to security. However, the question is, what if there are no idle cores in the multi-core processors that can be dedicated to security? We know that commonly used multi-threaded applications, such as web browsers and games, actually use multiple cores in the processors. Therefore, the assumption of finding idle cores every single time when enforcing a CFI policy may not actually be true. We evaluated a PT-based context-sensitive CFI mechanism on several systems, which is consisting of single core, 2 cores, 3 cores, and 8 cores. We use an Intel machine to perform our experiments, and as you can see, when we go from 8 core to 1 core system, the performance overheads of some of the benchmarks from Spec 2006 are increasing significantly. For instance, for H264F, it goes up to 651% from 378%, and on average, it goes from 22 to 41% from 8 core to 1 core system. This actually shows that if there's no idle core that can be dedicated to security when leveraging a PT-based CFI solution mechanism, we observe high performance overheads. But why do we observe this? To answer this question, we need to understand the design overview of processor trace. Processor trace is a hardware feature that can collect the change of flow information from the program that cannot be derived statically. For instance, the indirect calls, indirect jumps, returns, and conditional branches. When a process is running on your CPU, PT is collecting the control flow information in the form of encoded trace packets with a minimal performance overhead. On average, it is less than 3% overhead when collecting the traces. However, any PT-based CFI mechanisms need to decode this encoded packets using a software level decoded to obtain the reconstructed execution flow. And this decoding process or trace processing is orders of magnitude slower than the trace collection. How do PT-based context-sensitive CFI mechanisms prevent the excessive overhead of trace processing? Existing mechanisms offload the trace processing onto idle cores. Let's assume that we have 4 CPUs on our processor. This works use one CPU to run the process that they are trying to protect, another CPU to perform trace processing or packet decoding, and another CPU to perform ICD validation or to ensure that the current control flow targets, the targets of an ICT, comply with the statically generated CFG. So coming back to our previous question, why do we observe drastically increased performance overhead on a single core? Again, we present the same graph, the same experiment that we show in our previous slides, but this time we also present the packet count, generated packet count for each benchmark. And if you notice, some of the benchmarks generate higher number of packets, and actually these are the benchmarks that are affected by the single core experiment, meaning that when we switch from 8 core to single core system, we observe drastic performance overhead. The reason, as explained in the previous slide, is that packet decoding is actually putting a lot of pressure onto the single core, meaning that when we don't have any idle core that can be dedicated to trace processing, the performance overhead of the benchmark is increasing significantly. How we can improve PT-based CFI mechanisms? Similar to PT, we need to collect the traces efficiently by minimally affecting the performance of the protected program, and additionally, we shouldn't perform any packet decoding prior to ICT validation, unlike processor trace. In our work, we leverage a programmable hardware monitor called PHMON to achieve this goal. PHMON is a recent work which will be presented this summer in Unix Security, and it's a programmable hardware monitor interface with the RISC-V Rocket microprocessor through ROC interface. When a program is running on the Rocket processor, PHMON is collecting commit log, which includes several information such as the current instruction, the current program counter, the next program counter, and address and the data if we are monitoring a load or store instruction. PHMON consists of two components. It has a software interface where you can define monitoring rules and actions, and the hardware component, which are monitoring the events defined by the software interface. So what kind of events we can define? There are many of them, but I will provide two examples here. For instance, we can define an event to detect branch instructions in a program, or we can create an event which detects a program counter value when it is equal to a constant that we defined before, like a 0x800 in this case. Once we detect an event with PHMON, we can take follow-up actions in the form of an interrupt, an ALE operation, or a memory operation. For instance, upon detecting a branch instruction, we can write the source address of that branch instruction into a memory as a follow-up action, or when we detect a program counter value equal to 0x00, we can raise an interrupt. So in our work, we showed that we presented that PHMON can be leveraged to implement a state-of-the-art CFI mechanisms called micro CFI for two reasons. First, similar to processor trace, it can efficiently collect traces, and on top of it, PHMON doesn't require performing any decoding prior to ICT validation. PHMON, we implemented PHMON-based micro CFI to protect forward edges first, and to do that, we need to collect the contextual information that micro CFI requires. You can find more details about the contextual information that micro CFI requires in the paper. It's published in ACM CCS in 2018. In addition to contextual information, we need to collect indirect call and jump targets with PHMON. So we instrument the program to help PHMON collect this information, and whenever PHMON observes these values in the commit log, it performs a follow-up actions, which is basically writing these values into a memory region called micro CFI region. And whenever micro CFI region becomes full, PHMON driver, a kernel driver, copies the content of this region into kernel buffers. And finally, micro CFI monitor, which is a software level monitor in charge of validating the RCT targets, obtain the content of the kernel buffers to validate indirect call and jump targets and ensures that they are complying with the CFG. To show that forward edge protection is compatible with a backward edge protection, we also implemented a shadow stack using phmon. To do so, we programmed phmon to monitor the calls and returns. Whenever phmon observes a call instructions, it copies the next program counter into a shadow stack, and whenever phmon observes a return instruction, it pops up the recent value from the shadow stack and compare with the current return value. We evaluated both PT-based micro CFI and phmon-based micro CFI. For PT-based micro CFI, we use an Intel machine operating at 320 GHz, and for RISC-V, for phmon-based micro CFI, we use a 6-stage RISC-V rocket core prototype on an FPGA. We use spec CPU 2006 benchmarks to evaluate this two mechanisms. First, we show that phmon can efficiently collect traces similar to Intel processor trace. And on the left y-axis in this figure, you see the performance overhead, and on the right axis, you see the packet count, generated packet count for each benchmark. If you look at the packet-intensive H.264 benchmark, even that incurs performance overhead less than 5%, and on average, the performance overhead for trace collection is less than 1%, meaning that phmon actually can efficiently collect traces in their original forms without performing any encoding. Next, we evaluated both PT-based micro CFI and phmon-based micro CFI when protecting forward edges. In the blue bar, you see phmon-based micro CFI results, and in the gray bar, you see PT-based micro CFI results. As you can see, for packet-intensive benchmark H.264, the performance overhead of PT-based micro CFI on a single core is around 650%, while it is 274 for phmon-based micro CFI. The relative overhead of performance overhead is significantly lower in the case of phmon-based micro CFI, and the main reason comes from the fact that phmon-based micro CFI does not perform additional packet decoding prior to ICT validation. And as I mentioned before, we also protect the backward edges by implementing a shadow stack, and adding a shadow stack increases the performance overhead by less than 1%. In summary, Intel PT-based CFI mechanisms assume that there will be always idle cores that can be dedicated to security. And in this work, we show that when there is no idle core in the system, the performance overhead is increasing drastically up to 650%. And the main reason why we observe this increased performance overhead is originating from the software level decoding of PT. And to get rid of software level decoding, we leverage a hardware feature called phmon, which can efficiently collect the traces without incurring trace processing overhead, unlike PT. Here are my references used in this presentation, and you can reach me out at the provided email for your questions. Thank you for your attention.